Hi everyone. Today we're going to get acquainted with linear transformations. So let's start off with some basic definitions. A linear transformation is just a special kind of function that maps vector spaces to vector spaces. So instead of inputs and outputs being numbers, like the way we think of functions when we're talking about analysis, like in calculus, we're talking here about inputs and outputs being vectors. And they don't have to be the same dimension. That is, the vectors that we give as input don't have to be the same number of dimensions as the vectors that we get as output. So what we call a transformation in the context of linear algebra is really just a function. And when we're talking about a linear transformation, that's what I mean by a special kind of transformation. So let's call our transformation T. It's going to take vectors from Rn and map them to Rm. And these are the two conditions. So if we take any two arbitrary vectors v and w from this n-dimensional space that's the domain, and then apply the transformation to their sum, we should get the same thing as if we applied the transformation to those pieces individually and added them up. So a quick way of saying this is that the transformation of the sum is the sum of the transformations. And as I said, there are two properties that a transformation must have if it is to be called a linear transformation. So that's number one. And number two says that the following has to be true about any scalar r and any vector v. So this condition says that if we take the transformation of a scalar times a vector in our domain space, then we'll get the same thing as if we just took the transformation of the vector and then multiplied it by that same scalar over in the codomain space. So now we see that a transformation is linear exactly when these two conditions are satisfied. Let's have a look at some transformations and see if we can tell if they're linear or not. Okay, so here's an example where we have a transformation T that is mapping from the domain R2, so taking two-dimensional vectors, and it's mapping them into three-dimensional vectors, right? So it's taking an input of a two-dimensional vector and mapping it to a three-dimensional vector by this algorithm, right? So this is just the same kind of function notation like you saw in calculus, f of x equals, 2x squared minus 1, or something like this. Right now our input's a vector though. So this says that t of this vector is equal to this three-dimensional vector. So the first component of that is still the first component over here. Second component stays the same, and then the third one's just assigned to be this number 1. So now we can ask this question: is T linear? And remember, in order for T to be linear, it has to satisfy those two conditions right here, right? The transformation of the sum should be the sum of the transformations. And if we take a scalar r and multiply it by v, and then take the transformation of that, right? So take the transformation of r times an input vector, we should get the same thing as if we take the output vector and multiply it by r. So let's try this out. So if we take two vectors, a, b, and c, d, elements of R2, so they're two-dimensional vectors, and then let's compute the transformation of the sum. So T of AB plus CD. Now if I simplify the inside, I get A plus C and B plus D. Then if I apply the transformation, it says first component, second component stay the same, and then the third component's just 1. So I would get A plus C, B plus D, and 1. Now let's see what let me scroll back up here, and we'll see what the right-hand side of this equation looks like. So we just computed the transformation of the sum. Right? We computed the sum of the two vectors, AB plus CD, and then computed the image of them under this transformation. Now we have to ask, what does the right-hand side look like? Does it match? So we'll take the transformation of each of these two vectors individually and then compute their sum. So we know from the rule, right, the transformation of AB, so T of AB is equal to AB1. And T of CD is equal to CD1. The sum of these two things is this. It's AB1 plus CD1. And that's equal to A plus C, B plus D, and 1 plus 1, which is 2. And now we have to go back and ask that question. Here is our left-hand side. This is our right-hand side. Are these two things equal? Well, their first two components match, but their third one doesn't, right? This one is a 2 and this one is a 1. So this transformation fails to be linear by failing that first condition. So the answer to this question is no, it's not a linear transformation. We could check that other condition. It's also going to fail that, but just to see how we go about doing that, let's pretend that we need to check it. So we've checked condition 1 here. Let's check condition 2 now. The transformation of R times a vector, right? So this is just a scalar multiple, and this is the left-hand side of the property, right? We're going to take the transformation of R times AB. So that's scalar multiple, right? It's R times A, R times B are now the components. And if I apply the transformation, I'm going to get RA, RB, and 1. So this is what we just computed. The right-hand side of the property says compute R times the transformation of the vector. So R times T of AB. So the transformation of the vector AB is A, B, 1. And if I take that scalar product now, I'll get RA, RB, and R. And again, this is our left-hand side of the property and our right-hand side of the property. And these two things are not equal. Their first two components are the same, but their last one is not the same. So this fails to be a linear transformation in both of those ways. Now let's see an example of something that is a linear transformation. Here's an example of a transformation that is going to turn out to be linear. So let's check those conditions. So here I've set up the left-hand side of the first condition that asks us to find the image under this transformation of the sum of two vectors and check to see if it's equal to the sum of the images. So now I need to take the transformation R of this vector from R3. And I just want to point out that for the first component, we're going to have x minus y. So this is like our x, y, and z here. So we need to be careful when we're plugging in. We're going to get a plus d minus b plus e. And I'm going to put that b plus e in parentheses. And for our second component, we're going to get x plus z. So that's a plus d plus c plus f. No parentheses needed there. Okay, so that's our left-hand side of that first condition. And now let's write down our right-hand side. And now what we need to do is compute the images of these two vectors under this transformation. So if I do that, I'm going to get, let's see, R of ABC will be A minus B, A plus C. And then I've got plus R of DEF. That will be D minus E and E plus F. Summing these two things up, I'll get A minus B plus D minus E and A plus C plus E plus F. Now, since these two things are equal, condition 1 checks off. Now, since that passed, we're halfway there. We know that this transformation satisfies this linearity under the addition operation in this vector space, but we still need to check for scalar multiplication. So for our second condition, here's our left-hand side. And first we'll compute the scalar multiple inside. And the image of that under this transformation is this. And again, that's our left-hand side. And we need to check to make sure that it's equal to the right-hand side of that condition. So computing the image of ABC gives me A minus B and A plus C. And multiplying through by the scalar, I'll get R times A minus B and R times A plus C, which we can see pretty immediately is equal to the left-hand side of that condition. So since both conditions check off, we can say that this R is a linear transformation. In the next video, we'll draw some pictures and see how to describe a linear transformation in terms of matrix multiplication.